Welcome back to Linear Algebra. I'm Dr. Jeff Grove. Today, we're going to talk about determinants. Determinants are only defined for square matrices, and we're going to build these up from the determinants of 2 by 2 matrices. So we'll begin by defining the determinant of some matrix A equals A, B, C, D, a generic 2 by 2, is denoted by, now there are a couple different notations. One is flat bars on the sides. Another one is det of A. And defined by the determinant of the matrix A, B, C, D using flat bars is, by definition, so you're just going to accept this for now, AD minus BC. So you make the product down the main diagonal, and then you subtract the product going the other way. So for example, suppose that A is the matrix 2, 3, 4, 1. Then the determinant of A in this case is 2 minus 12 equals minus 10. Now that we've defined determinants for 2 by 2 matrices, how do we define them for 3 by 3s? Well, if you have a 3 by 3, we can calculate the determinant as follows. We can expand this using something called cofactor expansion. A11 times the determinant of the submatrix that you get by crossing out the column and row that contains A11. That will leave A22, A23, A32, A33, and then minus, and then A12 times the determinant of the matrix that you get by eliminating its row and column. That's A21, A23, A31, A33, and then plus A13 times the determinant of the submatrix that you get by crossing out its row and column. That's A21, A22, A31, A32. Notice the change in signs, plus, minus, plus. That was cofactor expansion around the first row. It's a theorem that you can use this cofactor expansion around any row or column, but you have to pay attention to the sign structure. There's a checkerboard pattern of pluses and minuses. So if we do cofactor expansion around the second row, we'll have to use these signs. We'll have minus A21 times the determinant of the submatrix that you get by crossing out its row and column. That's A12, A13, A32, A33, and then plus A22, cross out its row and column, A11, A13, A31, A33, and then minus A23, cross out its row and column, A11, A12, A31, A32. Suppose, for example, that A is the matrix 1, 3, negative 2, 2, 1, 0, and then 3, 4, and let's make this 0. It's to our advantage to do an expansion around the last column because of all those zeros. You'll have plus, minus, plus, the negative 2 times what you get when you cross out its row and column. And then a negative 1 times 0 times what you get, and then plus a positive 1 times 0 times what you get crossing out rows and columns. These other two terms don't matter because these two entries were 0. So we have negative 2 times 8 minus 3. To calculate the determinant of a 4x4 array or larger, we're going to formalize this whole process into a sequence of definitions. First of all, if A is an n by n matrix, so this only applies to square matrices, the ijth minor of A is denoted by m subscript ij and defined to be the determinant of the submatrix of A obtained by eliminating the ith row and jth column of the matrix A. So just cross them out and get the determinant of a submatrix. We've been using these in the calculation of the determinant of a 3x3. So for example, if A is 1, 2, 3, 4, 5, 6, 7, 8, 9, then M2, 3 is what you get by eliminating the second row and third column and taking the determinant. The ijth cofactor of A, which we're assuming is n by n, it's a square matrix, is denoted by Cij for cofactor and defined by Cij is negative 1 to the power I plus j times mij. This negative 1 to the power I plus j gives you the sign structure. So for example, if A is 1, 2, 3, 4, 5, 6, 7, 8, 9, then C2, 3 will be plus minus minus the determinant that you get by crossing out row and column 2 and 3. We can now define the determinant of an n by n matrix. Let's suppose A, for instance, is the matrix A11, A12 through A1n, and do AN1, AN2 to ANN. The determinant of A is denoted by determinant of A or determinant of A, and defined by the determinant of A is, we'll do a cofactor expansion around the first row. A11, C11, that's the cofactor, A12, C12, plus dot 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 plus A1n, C1n.
Let's calculate the determinant of this matrix. We have a 1 times the determinant of the submatrix that you get by crossing out its row and column, 0, 5, 3, 2. Then you switch sign and you add negative 3. It's going to be plus, minus, plus as we go across. Cross out its row and column, that'll be 4, 5, 1, 2. And then you add a negative 2 times what you get when you cross out the row and column. That's 4, 0, 1, 3. We get minus 15. 8 minus 5 is 3, times negative 3 is minus 9. And then 12 times negative 2 is minus 24. Negative 15 minus 9 is minus 24. Minus 24 gives you minus 48. There is a special method for calculating determinants that only works 3 by 3s, like this. I'll show you how that's done. Some people like to copy the first two columns. I'll show you how this is unnecessary in a minute. And then you multiply down little diagonals. 0 plus 15 plus negative 24, and then you subtract products going the other way. Minus 0, minus 15, and then minus 24, which is minus 48. You don't really have to copy the last two columns. All you have to do is keep track. There has to be 3 factors in every diagonal product. I'll show you how to do that. You continue to multiply down by diagonals, but if you get down to the end of the matrix, you have to wrap back so that you get 3 in the product. And up here we have negative 2 times the 12, that's negative 24. Going back up the other direction, you subtract 0. You have to get 3 in each product, so it's going to be minus 15 and then minus 24. Keep in mind, this only works for 3 by 3s. It does not work for 4 by 4s or higher. One can also calculate the determinant on your calculator. Let's enter the matrix first by editing the matrix. It's going to be a 3 by 3. And what was that? 1, 3, negative 2, 4, 0, 5, 1, 3, and 2. That was the array. Now, second quit. Going to go back to second matrix. This time we're going to go to math, the math column. The very first one is the determinant. We need to enter the matrix that we want to calculate the determinant of. That's number 1. And minus 48. There it is.
You know what an upper triangular or a lower triangular matrix is. If I have, for example, A equals 1, 3, 2, 0, 2, 4, and then 0, 0, let's say 5, what is the determinant? You can see that we get the determinant of A is 1 times the determinant of 2, 4, 0, 5, and then we get minus 3 times the determinant of 0, 0, 4, 5, and then plus 2 times the determinant of 0, 2, 0, 0. These last two determinants give you 0 because we have a whole column of zeros. Here we get 10 minus 4, and we just get 10. Notice, 1 times 2 times 5 is 10. Is that always going to be true for an upper triangular matrix? and a lower triangular matrix, and for that matter, a diagonal matrix? For any of these, do you always get just the product of the diagonal elements? The answer is yes. We'll state that as a theorem. If some square matrix A is upper or lower triangular or diagonal, then the determinant of A is A11, A22 to ANN. That's the product of these diagonal elements. We can prove that by math induction. The smallest case is the n equals 2 case, and if we have A, B, 0, C, you get A times C minus 0. So you get the product of the diagonal elements. So it's true in the smallest case. Suppose the theorem is true for some n, then let A be n plus 1 by n plus 1. We're going to suppose A is lower triangular, so it has non-zero entries below the main diagonal and zeros everywhere else. If we do this cofactor expansion business, most of the coefficients of the cofactors will be 0. Then the determinant of A will be A11 times the cofactor 1, 1, which is A11 times the minor, since you're in the plus position at the upper left. Now the minor is n by n, and the minor, if we cross out this row and column, is still lower triangular. It follows by the induction hypothesis that since the theorem is true for n by n matrices, that this will in fact be A11 times A22 through A n plus 1, and the theorem is over. We need a theorem that tells us how determinants react to elementary row operations. If matrix A and B are related by a single row interchange or a single column interchange, except rows I and J are switched, then the determinant of A will be minus the determinant of B. The effect of switching two rows in a matrix, or two columns for that matter, is to only alter the determinant by the sign. If A is n by n, and B is obtained from A by multiplying the ith row by a constant C, then what is the determinant of B? Nothing more than C times the determinant of A. So the effect of multiplying any row by a constant is to multiply the determinant by that constant. If A is n by n, and B is obtained from A by multiplying the ith row by C and adding the results to row J, then the determinant of B is affected how? The answer is not at all. So the third elementary row operation does not change the determinant in any way. To prove this theorem, I'd like to prove the following lemma. The determinant of A can be calculated through expansion about any row or any column. We've defined the determinant of A to be A11C11 plus A12C12 through A1n C1n. But this lemma claims you'll get the same thing if you take AI1 CI1 plus AI2 CI2 for any row, the ith row. But you also get the same thing if you take the determinant as an expansion around any column as well. A1J C1J plus A2J C2J plus ANJ CNJ. For proof, you'll have to wait for upper division linear algebra. Sorry. The proof is by mathematical induction. The smallest case is the n equals 2 case. So let's compare ABCD with CDAB. In the first case, we have AD minus BC. In the second case, you have BC minus AD. When you reverse the order of the subtraction, you get a minus sign. So this is minus the determinant of ABCD. And the theorem is true in the n equals 2 case. Now the proof for part 1. Part 1, suppose B is obtained from A by swapping the ith and jth rows. So the determinant of A can be found by cofactor expansion, let's say, about the ith row, AI1 CI1 plus AI2 CI2 plus AIN CIN. The determinant of B can be obtained by cofactor expansion around the jth row, which gives BJ1 DJ1 plus BJ2 DJ2, where here we're denoting the cofactors of B by D's. But keep in mind, the matrix B was obtained from A by swapping the ith and jth rows, so BJ1 is AI1. But think about the relationship between Ci1 and dj1. They're the same, except perhaps for a rearrangement of the rows. That's the only difference. Let me give you an example. Suppose I have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Think about the cofactor C11. Well, that's just 5, 6, 8, 9. If we look at the matrix 4, 5, 6, 1, 2, 3, 7, 8, 9, then D2, 1, we're switching the first and second rows, will be a minus because we're in a minus position in our checkerboard pattern of pluses and minuses. 5, 6, 8, 9 by crossing out the column and row. So you get either exactly the same minor, or the minor could be rearranged. Let me give you an example. And it's either plus or minus depending upon the position. If we had swapped the last row with the first, and then did the cofactor expansion around the last row, on this first cofactor, D31 would be plus minus plus, and then we'd have 8, 9, 5, 6. So if you get a plus, then the rows are swapped. If we had a minus out front, then the rows were not swapped. Either way, you're going to get a change in sign between the Ci1 and the dj1. They're going to have opposite signs. Otherwise, they just have the same rows. The rows might be rearranged, but the only difference will be a plus or a minus sign. So continuing this calculation, the determinant of B is minus AI1 Ci1 minus AI2 Ci2, and then AIN CIN, which gives you minus the determinant of A. On part 2, suppose you're taking the determinant of A11, A12, A1n, and suppose the only difference is on the, say, the ith row, CAI1, CAI2. You multiply everything through by a constant C. The way to do this would be to calculate the expansion around the ith row. C times AI1 CI1 plus C times AI2 CI2 plus C times AIN CIN, and you can factor the constant C out and just get the determinant of the matrix A. For part 3, we'll suppose that the matrix will have on the jth row a J1 plus C a I1, a Jn plus C a In, and then a N1 through a Nn. In this case, we'll do the cofactor expansion around the jth row. When we do, we'll have a J1 plus C a I1 times Cj1 plus a Jn plus C a In Cjn. We'll distribute. When we distribute, we obtain AJ1 CJ1 through AJN Cjn, and then C times AI1 Cj1 through AIN Cjn. This first grouping is the determinant of A, plus C times the determinant of a matrix where the coefficients in the jth row are the same as the entries in the ith row. So you'll have AI1 through AIN, and then on the jth row you have again AI1 through AIN. So this is on the ith row, and this is on the jth row, a repeat. But if you have two rows that are the same, you can swap those rows and you should get a negative. But if you get a negative and it's actually the same thing, that implies that if you have two rows that are repeated, the determinant must be 0. You get the same thing if you swap the rows, but if you swap any two rows, you're supposed to get a minus by part 1 of this theorem. It follows that this determinant is 0, and the answer is the determinant of A. This last theorem will really help us out if we're calculating the determinants of big matrices. So let's give an example. Suppose I'm calculating the determinant of 1, 2, 0, 3, negative 2, 1, 0, 5, say 3, 1, 2, 4, and negative 1, 0, 1, 0. We can perform elementary row operations on this, and it will not change the determinant. So for example, what if we do 2 times row 1 plus row 2 yields a new row 2? Negative 3 times row 1 plus row 2 yields a new row 3 yields a new row 3, and then row 1 plus row 4 yields a new row 4. That doesn't change the first row at all. 2 times this plus this gives us 0. 2 times this plus this, 5. 2 times this plus this. 2 times 3 is 6 plus 5 is 11. Negative 3. Negative 3 and 3 makes 0. Negative 6 and 1 makes negative 5. We'll have 2. And then negative 9 and 4 makes negative 5. 1 and negative 1 is 0. 2, 1, and then 3. Now we can continue these elementary row operations to introduce more zeros. But right now we can do a cofactor expansion around the first column. That's going to give us a positive 1 times 5, 0, 11, negative 5, 2, negative 5, 2, 1, 3. Continuing these elementary row operations, why don't we take negative 2 times row 3 and add it to row 2. That'll put a 0 in this middle spot. That leaves the last row alone, but we're doing negative 2 times 2 is negative 4 plus 5 is negative 9. We'll get a 0 in this spot by design. Negative 2 times 3 is negative 6, and negative 5 makes negative 11. We can now do cofactor expansion around the middle column, plus minus plus minus. We'll have minus the determinant obtained by crossing out the row and column containing 1. That's 5, negative 9, 11, negative 11. Remember that we can factor constants out of any row or any column. We can factor 11 out. So we'll have negative 11 times negative 5 plus 9. 9 minus 5 is 4 times negative 11 is negative 44. You can see that by introducing a lot of zeros into the matrix, we've greatly simplified the total number of calculations that were required. In addition, you can factor constants out of any row or column. Factoring the 11 out made the arithmetic simpler for us. There are some observations that we should make and codify in a theorem. First, if any two rows of a matrix are the same, then the determinant is 0. Or columns. If one row consists entirely of zeros, then you can do cofactor expansion around that row and clearly get 0 for the determinant. If one row of a matrix is a constant multiple of another, then you can use the third elementary row operation to make that constant multiple row equal all zeros. That means the determinant must be 0. Same is true for any column. The determinant of the transpose of a matrix is the same as the determinant of the matrix. This is pretty easy to see. The cofactor expansion around the first column of a transpose will equal the cofactor expansion around the first row of A. So you get the same thing. The determinant of a constant times a matrix. Multiplying a matrix by a constant multiplies every single row by that constant. According to the last theorem, if you multiply one row by a constant, that constant can be pulled out of the determinant. Here you'll have to pull that constant out of every single row of A. That means you get c to the power of n times the determinant of A. Now, the determinant of matrix A times matrix B is the determinant of matrix A times the determinant of matrix B. This seems less obvious. We definitely require a proof of property 6. Property 7 is an immediate consequence of property 6. The determinant of A to the power n is the determinant of A to the power of n. Unfortunately, the proof will have to come later in our theoretical development. For now, let me just show you an example. Suppose A is the matrix 2, 3, 0, let's say 5, and B is the matrix 1, 2, 4, 7. Then the determinant of A will be 10, and the determinant of B will be 7 minus 8, which is minus 1. That means we are expecting the determinant of A times B to be negative 10. What is A times B? We'll have 2 and 12 makes 14. 4 and 21 makes 25, 0 and 20, followed by 0 and 35. You can see then that the determinant of AB is 14 times 35 minus 20 times 25. I don't know about you, but I like to do my arithmetic by factoring as much as I can out first. I can factor a 5 out of both terms. I can also factor a 2. Notice I have 10 outside now. 10 times 49 minus 50. That's negative 10. There is another theorem that we can prove from all of this. A is invertible if and only if the determinant of A is not 0. This is an if and only if proof, so we're going to have to prove both directions. Suppose A is invertible. Then A inverse exists, and A times A inverse is the identity matrix. It follows then that the determinant of I, which is 1, it's triangular, it's diagonal, so the determinant is the product of the diagonal elements, is the determinant of A times A inverse, which is the determinant of A times the determinant of A inverse. It follows that the determinant of A can't be 0, because if it were 0, you wouldn't get 1. We now need to prove this the other way around. This is the theorem where if determinant of A is not 0, then A inverse exists. We're going to prove this by contrapositive. It's important that you know what the contrapositive of a statement is. If I have a statement A implies B, then the contrapositive is not B implies not A. Let me give you an example. Suppose A implies B is the statement, if I am in Paris, then I am in France. The contrapositive would be, if I am not in France, then I am not in Paris. You can see that a theorem and its contrapositive imply each other. If it is a true theorem that if I am in Paris, then I am in France, it will also be true that if I am not in France, then I am not in Paris. And vice versa, by the way. It's possible to show, and it's always shown in a course in mathematical logic, that a theorem and its contrapositive are logically equivalent. That's not true for the converse. B implies A is called the converse. If I am in France, then I am in Paris. That's not necessarily true. There's also the inverse, not A implies not B. If I am not in Paris, then I am not in France. That's not necessarily true either. But a statement and its contrapositive are always logically equivalent. So if you can prove one, then the other one must be true too. The contrapositive of our statement is, if A inverse does not exist, then the determinant of A is 0. Now, we know something about the calculation of A inverse, and when it exists, and when it doesn't. If A inverse doesn't exist, then in that process of trying to find A inverse, you end up with a row of zeros. In other words, if A inverse does not exist, then A is row equivalent, meaning there's a finite sequence of elementary row operations that you can perform on A, to a matrix with a row all zeros. If that's true, that implies that the determinant of A is 0. And the theorem's over. As an immediate corollary, we have the following. The determinant of the inverse is 1 over the determinant of the matrix A. That followed because 1 was equal to the determinant of A inverse times A, which was the determinant of A inverse times the determinant of A, and then you just divide. I want to make a list of things that are equivalent. The following are equivalent, and sometimes mathematicians will say TFAE instead of saying the entire phrase. The following are equivalent. 1. A is invertible. That means non-singular, which means A inverse exists. 2. That's equivalent to AX equals B has a unique solution. If A inverse exists, you can easily calculate it. X is A inverse times B by multiplying both sides of this equation on the left by A inverse. Consider the homogeneous system AX equals 0. We know this always has a trivial solution, but if A is invertible, then the trivial solution will be the only solution. As we've seen, if A inverse exists, then in the process of going from A abutted to the identity matrix and finding the reduced row echelon form, you end up with the identity matrix and then A inverse on the right. That means you can perform a sequence of elementary row operations on A and reduce it to the identity matrix. So A is row equivalent to the identity matrix. To these, we can add one more important equivalence. The determinant of A is not 0. Now, we're just getting started adding to this list. So far, we have 5 equivalent statements. We're going to have a much larger list as this course goes on. We're going to introduce a new method for solving systems of equations called Kramer's rule. New to this course so far, anyway. In Kramer's rule, we're going to solve linear systems. Let's suppose we have x plus y equals 3, 2x minus 2y equals 1. Kramer's rule says you can get the solution immediately. The x-coordinate of the solution will be, the denominator will be the determinant of the coefficient matrix. The numerator will be the same determinant, but with the x coefficients replaced by the right-hand sides. Negative 6 minus 1 is negative 7. Negative 2 minus 2 is negative 4. So the x-coordinate of the solution is 7/4. The y-coordinate of the solution has the same denominator. The numerator will have the determinant with the y coefficients replaced by the right-hand sides. This gives us 1 minus 6 is negative 5. And so we have 5/4. X plus y. If I have 7/4 plus 5/4, I get 12/4, and that's 3. 2 times 7/4 is 7/2, minus 5/2 gives us 2/2, or 1. So this surely is the solution. 7/4, 5/4. If the system of equations is only 2 equations and 2 unknowns, Kramer's rule gives you an excellent way of solving the system by just writing the answer down right away. If the system has more equations than 2 and more variables than 2, this becomes increasingly unwieldy. It's worse and worse the larger the system. In fact, Kramer's rule might be the best way to solve a system of 2 equations and 2 unknowns, but the worst way to solve bigger systems. As a quick example, let's solve, at least for the x-coordinate of this particular system. The denominator will be the determinant of the coefficient matrix. The numerator for solving for x will replace x coefficients by the right-hand sides. We can calculate these 3 by 3 determinants more simply if we perform the third elementary row operation to introduce as many zeros as we can. For instance, we might take negative 2 times the first row and add it to the second row. Negative 2 times this plus this. Negative 2 times negative 4 is positive 8, plus negative 2 is 6. Negative 2 times this plus this. Negative 3 times the top row plus the third row gives us a 0 in the lower left. Negative 3 times negative 4 is positive 12, and 2 makes 14. And then negative 3 and this gives us 1. We can do the same thing in the denominator. Negative 1 times this plus this. Negative 1 times this plus this. Negative 1 times this plus this. If we take negative 1 times the second row in the new denominator and add it to the third row, we'll have 0 and then 1. That will make the matrix upper triangular, and the determinant will be 1 times 2 times 1, or 2. In the top, if we do a cofactor expansion around the first column, we'll just end up with the determinant of the submatrix 6, 2, 14, 1. That's 6 minus 28 divided by 2. 6 minus 28 is negative 22 divided by 2, and we get negative 11. I think you can see that this becomes a bigger and bigger amount of work the bigger the system gets. We're going to consider the system AX equals B in its matrix form. Let A sub I be the matrix A with the ith column replaced by the right-hand side's B. Then x sub I in this system, the ith coordinate of the solution, will be the determinant of A sub I divided by the determinant of A. The proof of Kramer's rule is kind of elegant. First of all, recall that the identity matrix is E1, E2 through En, where E1, you'll recall, is 1, 0, zeros, E2, 0, 1, 0, and so on. Now, let I with the subscript of I be I with the ith column replaced by x. I want to look at A times I sub I. Remember, this is A times E1. The ith column is replaced by x. Here's the ith column, and of course it ends in En. When you multiply a matrix in its column form like this, you end up with A times E1. On the ith column, we'll have A times x. A times the identity matrix itself is just A. A times E1 gives you the first column of A. So we'll have the first column of A, which I'll denote by A subscript 1, A subscript 2, but AX is equal to B. So the ith column is replaced by B. This is A sub I in our notation in the statement of the problem, where you take the matrix A and replace the ith column by the right-hand sides. So we have for sure that A times I sub I is A sub I. Now that implies that the determinant of A times I sub I is the determinant of A sub I. And on the left, that's the determinant of A times the determinant of I sub I. We're assuming the determinant of A is not 0, so the determinant of I sub I is the determinant of A sub I divided by the determinant of x. The only question that remains is, what is the determinant of I sub I? The determinant of I sub I is the determinant of the matrix with, let's see, 1, 0, zeros, 0, 1, zeros. We had the ith column replaced by x1, x2, through xi, through xn, and then continue on 0, 1. How do you calculate the determinant of this matrix? Well, you do this through the ith row. On the ith row, almost every single entry will be 0, except for I sub I. And then every entry after that will be exactly 0. So you get on the ith row of the ith column, if you do the cofactor expansion through the ith row, you get x sub I times its cofactor. We're doing this ith row, ith column. I plus I will be the sign of the cofactor. And then you'll just have the determinant of the submatrix that you get by crossing out the ith row and the ith column. But that's going to be an n-1 by n-1 identity matrix, which will have determinant 1. I plus I is 2i, which means we have an even exponent. So this is also 1. So we just get the ith coordinate of the solution. So the ith coordinate of the solution will be the determinant of A sub I, where we replace the ith column by the right-hand sides, B, divided by the determinant of A. And that's the end of the proof of Kramer's rule. I got a kick out of using Kramer's rule in one little step in my dissertation. You never know when you might need this stuff. When we started out with this definition of determinant, it may have seemed rather abstract. However, Kramer's rule says you can use these determinants for solving systems of equations. You can use them for a lot of other applications too.